only put my trusted code in these SIRs. So recently there was work on building sensitive data analytics using Intel SGX instructions, where only the map and the reduce functions had access to sensitive data, and the rest of the Hadoop stack was untrusted and was responsible for doing untrusted things like scheduling of resources and so on, and didn't have access to any sensitive data. Of course, while we have the CPU giving us guarantee that these SIRs cannot be, for any code to be useful, it needs to do I/O. Will take place by where the SIR is going to, in the case of VC3, it's going to Hadoop's memory. So in this case, we have to communicate with each other. For example, sending key. These mappers and reducers are going to encrypt these key value pairs and then compute it on. But unfortunately, like most programs, SIRs are hard to, such as memory safety issues. An example being a heartbleed bug from the SIRs. Or the SIR may itself have its own set of bugs. It could make optimizations that compromise your security guarantees. So the goal of our work is to study how we can develop these SIRs securely, how that the secrets are never leaked from the SIR, make such programming errors, or we may use buggy compilers. So let's look at what could go wrong and what are some of the challenges that are needed or that are involved in proving confidentiality. So let's look deep into the implementation of a reduce method from the VC3 effort. So first, since the reducer is going to decrypt the key value pairs, we need a way to provision a encryption key within the SIR to decrypt them. Next, the key value pairs will be brought from outside and decrypted, and then computed on, serialized onto a buffer called clear text, encrypted and sent outside the SIR. So first, the developer needs to make sure that the it securely. Next, there's a call to sprintf to serialize the result. And sprintf is notoriously known for causing memory safety issues. For example, if the programmer has performed buffer overflow exploits, overwrite the return address, for example, on the stack, and cause a whole sort of control flow exploits. And it's very hard to give guarantees from there on. Next, we want to encrypt the result. So for this to be secure, we need to make sure the AES key has not been accidentally leaked or modified. And finally, the encrypted result is sent out to untrusted memory. And in fact, anytime your code is writing out values, you need to make sure that it's safe, that it's either encrypted or its value is independent of secrets. And that kind of analysis requires us to precisely track the flow of secrets within SIR memory. And in our previous work, we found that such analysis is very hard to scale at the machine code level. Finally, all of this code will be compiled using a compiler, which may have bugs. So our solution is as follows. We're going to partition our SIR into two parts, a verified runtime library and a user code that's going to be provided by the developer. The runtime library will take care of a lot of the code, for example, by implementing a send and a receive API. So in order, the user can invoke a send of encrypting it and sending it out to the untrusted memory. Instead of considering arbitrary user applications that we want to put some constraint. We want to make sure that the user code doesn't modify untrusted memory on its own, that it has to interact with the external world through this send API. With this design, the code from the previous slide, the key value pairs can be brought in using invoking. And instead of dealing with encryption, the encryption for you. And the separation of concerns here, crypto keys or have to manage them, nor does you direct untrusted memory. The writing to untrusted memory it happens within L. And that should hopefully make the reasoning of. So there are a couple of interesting implications. User code satisfy this IRC property. For the runtime library is encrypting all of the messages for you, you essentially get protection against explicit information leaks. Of course, we don't guard against implicit leaks or several side channels. And we are not really going for full functional correctness. It's forced to only ever interact with the external world through the send API, which will encrypt everything for you. So even if the adversary only ever sees encrypted values in an exploit, which is a nice guarantee to have. And also don't really care about how the user code manages memory. In fact, we can treat all of you to have secret values. So IRC is a very nice property to have, but how do we go about proving it? Well, it basically boils down to the runtime library and also some checks that we need from you. For L to be correct, basically the send and receive must be implemented securely with nice cryptographic guarantees. U needs to play nicely with L. It cannot start executing arbitrary instructions within L. It has to interact with it through API entry points. And this is not necessarily trivial because U and L are executing in the same privilege level. And finally, we don't want you to bypass the runtime library and start writing to untrusted memory. It should not be doing any writes directly. And just as I mentioned before, these are the only two constraints we need from the user code. We don't really care about full functional correctness. And in fact, because we don't care about how U manages its secrets, our proof doesn't really require any annotations from the developer. And as we will see later, we actually the user to write invariants in the program. We formally specify property, and we show how it's a nice intuitive. We show how IRC can be proved by decomposing. We have built a fully properties that I mentioned before. Next, we'll identify some properties we need from the runtime library, and finally conclude with some evaluation. So the first property that we need you to satisfy is that it plays nicely with L. That it only interacts with L via these API entry points. And this may sound like an easy property to enforce, but it's actually fairly non-trivial in practice. And that can be this program. And this is fairly representative of the problem a few slides ago. So we have a programmer trying to buffer by adding the base. So now the adversary can make Q point to the return address. Q is dereferenced to write some other value. And this allows an adversary to make the return location in the code. And it could be some arbitrary code, such as instructions, which can happen because x86 instructions have very. It can just make it point to some arbitrary instruction in L and not necessarily. And finally, as soon as you invoke the return instruction, arbitrary code, and now you are running arbitrary instructions, and all guarantees are lost. So to deal with this problem, what we need is some notion of control. And that's formalized as the following constraints. We need all call instructions in the code to always target a procedure within U or an API entry point of L. Back to the caller. And this property was violated in the program we saw above. And finally, we require jump instructions to target a legal instruction within the procedure, not in the middle of an instruction. We also allow tail calls, but that's a side note. And CFI has been heavily studied in literature. There are standard definitions, and we claim that our definition is slightly weaker than the standard notion of CFI, and that's because we can allow calls to go to any procedure in U. We don't really need a call to target the procedure that was intended in the source code. But even though this is weaker, we show that it's enough to give us the property we want, which is that U interacts with L only via API entry points, which, as you can see, follows directly from the first constraint on the call instructions. Now, while weak CFI is a nice property to have, the code that the developer writes may not satisfy the property. So wouldn't it be nice if we can actually transform the untrusted code from the developer to actually give us this guarantee? And we'll do just that using certain runtime checks. So we'll use a compiler that was developed as part of the VC3 effort to introduce certain runtime checks in the code. And the way the runtime checks work is as follows. It introduces a bitmap that keeps track of what areas in memory are safe to write to. So things like return addresses should never be written to, and hence it's marked non-writable in the bitmap. Whereas writing to local variables or objects on the heap are not going to compromise control flow integrity, and those are marked safe to write. So in the presence of these runtime checks, the execution proceeds as follows. The programmer computes this pointer, which is still allowed to point past to the buffer onto the return address. But as soon as this store instruction tries to execute, the runtime checks take place, and they essentially cause a software exception to happen, and execution doesn't proceed anymore. Now, we are using a compiler to introduce runtime checks that enforce weak CFI, but it would be nice if we don't have to trust the compiler, and that's mainly because the compiler in our case is Visual Studio, and there may be any number of bugs in Visual Studio. And also, in practice, the compiler will optimize many of these runtime checks for performance reasons. So what we're going to do is verify the output of the compiler. We'll take the x64 machine code produced by the compiler, and we're going to formally model it in a verification language, which happens to be Boogie in our case. And this is a fairly detailed modeling of the code. As you can see, we are modeling details such as status flags in the CPU. And another thing I don't want you to focus on the details of the model, but one thing I want to between instructions produced as were coming basically from the trust the compiler. About the Boogie model, we need to think about so since the adversary gets to control, we need to make sure that every time we if the address happens to be from untrusted memory, then we get a garbage. Transforming loads in our Boogie model to be the following. It's an if then else. If it loads from SIR memory, you get the correct value, else you get an unconstrained symbolic value. And in our previous work, we showed that this modeling of loads is sound in that any behavior you can have in the presence of a privileged OS level adversary is captured by doing this transformation. And so, and the OS and this adversary model allows the OS to do interrupts at any point in time, modifying page tables arbitrarily, or launching other SIRs in the system. Now, with this transformation, we are guaranteed that any property we prove on our Boogie model is now going to hold even when SIR is executing in the presence of an adversary. So we take that instrumented Boogie model, and to satisfy weak CFI, we are going to introduce proof obligations at interesting store instruction or the return instruction. And while I haven't yet described to you what these proof obligations look like, design them is such that they indeed give us weak CFI. If all the proof obligations, then you get this property. And weak CFI is needed because, as you may recall, we need you to only interact with L using the APIs. We take these proof obligations and we throw it to an SMT solver. And an important thing to note is that empirically, we find that the main reason we are able to prove these properties using SMT is because there are runtime checks in place, and often they are local to the proof obligations. So a solver oftentimes only has to do some local reasoning in order to prove that the code is doing safe things and the proof obligations hold. So let me describe to you one example of what our proof obligation looks like. A reduced example from before, it's calling sprintf, And sprintf receives a buffer as input called clear text, and the code expects sprintf to write to this buffer, which means that the bitmap should make sure that the clear text buffer is marked writable. It introduces certain code to update the bitmap and make clear text writable. Applications needs to make sure that the compiler is doing its job correctly, that only to make the clear text writable and not, for example, accidentally making the return address. We have similar proof obligations for a lot of other returns and indirect jumps and so on. We're not going to go over that today, but the guarantee that we get is off, if all the proof obligations are discharged by the SMT solver, then we do get weak CFI. And we have a machine-checked proof of soundness for this. So we took care of our first property. Now the second property on U is that it doesn't bypass the runtime library to write outside the SIR. So we'll illustrate that. We can have a developer put this code such the pointer now points past the SIR memory onto untrusted memory. It tries to write out a secret, the adversary gets to view that. Now, just like before, we're going to protect against these kind of issues by using our compiler to put in runtime checks. Says whenever you do a store, the address in SIR memory. And as soon as you execute that store instruction, a software exception will happen as before, and it will prevent further execution. Compiler, similar to before, we are going to add a proof obligation that says that for any store within the user code. So previously, proof obligations for weak CFI, and now I've given you proof obligations needed to make sure writes are within SIR. Gave us the property that we wanted, which is IRC, and that property states that all interactions runtime libraries send API. Now, I've given you a set of take our entire user code and prove these proof obligations. We could do a global verification, but wouldn't it be nice for scalability if you could analyze each procedure within U on its own? And we would like to do that also without incurring any false positives. So the way we are going to do this is by having the compiler generating enough to make this feasible. And I'll show you with this example. So again, you have a reduce calling the sprintf function, which will write to this buffer called clear text. Now, clear text lives within reduce's stack space, which is guaranteed to be within SIR memory. Even then, a compiler is going to make sure that that is indeed the case by using runtime checks to check that the buffer being written to is within SIR memory. So with this runtime check, sprintf on its own without its calling context. Finally, we need some correctness properties to hold on our runtime library, and they are as follows. First, make sure that they don't start attacking you. So since L and U execute in the same, it's attacking you, like for example, writing to some return addresses and that are, then all guarantees are lost. Since send and receive are doing crypto, we want to make sure that the channel key is never accidentally modified or leaked, and so on. We'll for malloc and free, that is also implemented. And one thing I would like to point out is that we don't have any required clauses. And the reason for that is because we want to all sorts of applications, which means we can't really have any specific preconditions that we want from a user code. Yeah. So finally, I'll show you some evaluation. Of course, for ease of verification, we are paying for it in using runtime checks. And the VC3 developed showed that these runtime checks incur as follows. We take 3 benchmarks. The first 3 benchmarks, last 3 are spec benchmarks. And then And we generate several thousands for each of these benchmarks. And but even after fighting with the SMT solver, we found that some of the assertions, and the reason is that there are large procedures in some of these spec benchmarks that are 700. The corresponding boogie model is about 5,000 statements long, and these models make quantifiers, which make SMT reasoning hard. Another thing I want to point out is that positives, we did encounter a benchmark to have one of the benchmarks having 4 false positives, and we later found out that the compiler was doing a global optimization in a rare case where it was removing the method somewhere, and we discovered and to deal with these false positives, we can simply. And another nice thing is that one of our benchmarks 0 timeouts and 4 hours of machine time on an 8-core machine to. Most of these proof obligations are fairly. Within the first 10 seconds, 95% of our assertions are. Out of those cases, the solver is doing fairly local reasoning. But of course, there are some queries that do take a long time. Now, there's a lot of very interesting related work. One of this is, in our past work, we tried to do something similar. We tried to verify confidentiality properties of SGX program using a refinement type system for guaranteeing non-interference. But what we found out is that tracking secrets in memory, especially at the machine code level, was extremely expensive. And it also required global analysis in that case. And we found that to be very hard to scale. There's a whole lot of amazing work on doing information flow analysis for some in the session, and I'll just sample one of them being GIF, which tries to do information applications, again using a type system for doing non-interference. While GIF gives us a very strong guarantee of non-interference providing, the compromise is the entire Java language runtime is in your trusted computing base. There's a lot of interesting work on, for example, ironclad apps, which tries to do full functional correctness of applications using essentially deductive verification. And the comparison there is that it requires a lot of manual effort to guide the theorem prover in producing these proofs, whereas we are going for full automation. Now, a very related work is on software fault isolation. So in this specific work, the goal was to build a native client checker in the Chrome browser, which downloads untrusted modules and proves that they don't compromise the Chrome browser. And the difference here is that we are going for confidentiality, which is a slightly different goal, and it makes our verification, our proof obligations very different in nature. So in conclusion, we propose IRC as an intuitive design principle for building SIRs, which is, hopefully, as I've shown, it's easier to verify than doing full functional correctness. And it also avoids the expensive tracking of secrets in memory, which is expensive to do at the machine code level. We have built a fully automatic and modular verifier that operates directly at the SIR level, and it gives guarantees against the privileged OS level adversary. And we do all that with a very small trusted computing base that only includes the verifier and the CPU. And all of this is available on GitHub for you to play. But that's the end of my talk. Thanks.
Hi, Rohit. Nimrod Partush from the Technion. So 2 questions. First of all, I couldn't make out if your approach is like how it would handle return-oriented programming, whether it would be able to handle that. And if you answer that first, and then ask the question.
Okay, so it definitely handles return-oriented programming. So our weak CFI property was designed to prevent attacks like that. But of course, there are a whole set of attacks like jump-oriented programming, call-oriented programming that try to do something similar, that exploit the control flow. And what we have shown is that our weak CFI property no matter what happens, you're still guaranteed that it ensures that IRC is not violated, that you only call send to L via API entry points. So, of course, full control flow integrity may handle
Yeah.
some niche cases of control flow
Right.
exploits.
So you're saying it might interfere a little bit with control, but with control flow, but not
Yeah,
compromise.
so specifically, we don't care where the calls are happening. A call must target any procedure, whereas standard control flow would say that the call will go to the one intended as the source code. But what we've shown is that it doesn't, we don't really care about that because we are guaranteed that it will not jump arbitrarily within the runtime library.
Okay, great. And the second question, I really like the idea of like going from the binary back to a verification language to verify that the compiler didn't compromise the program. Do you have any plans to like do more work for checking this kind of compromisation, or do you know of previous work, or we should take this offline?
Are you referring to previous work on doing machine code analysis?
Well, on just verifying that compile optimizations didn't compromise the source code.
So I mentioned that this. There is work on fault isolation, where the goal is that you introduce runtime checks within your runtime checks within the binary, and they basically guarantee that the code doesn't do unsafe things. And of course, there is an independent verifier that does prove that the property indeed holds. But the nature of our runtime checks is different. It actually gives stronger guarantees. I didn't have time to go into that, and yeah, I can talk offline if you
Okay,
like. Yeah.
great, thanks.
So I was wondering what the formal guarantee of the system that you're building is for. What are the guarantees? Because at one level, it looks like the most natural one seems to be that the threat model is that everything except you can be compromised, right? Anything outside can be compromised, and but if you do that, then you would expect not to verify you in any way. You would say you is kind of free, and then when you verify you, you have this weak control flow integrity, which seems like an approximation of something. It doesn't look like it would guarantee it would be required to guarantee any formal property. So what is the actual formal property that you can ensure?
The property we want is information release confinement, IRC, which essentially guarantees that. So to prove confidentiality for an arbitrary application that does reads and writes is harder than showing IRC, which says that all of the writes happen through this interface that we have provided. And that allows us to do other things like, at the very least, if you encrypt it, you guarantee that all writes will be ciphertext values.
So I understand that, but globally, what is the guarantee? It's like from the. I know you're doing the IRC thing, but what does that guarantee? Eventually, what do I get at the end?
You're guaranteed that you'll never see plain text secret values in the untrusted regions, which could be your Hadoop application, it could be your operating system hypervisor layers. Nowhere do you see plain text secret values.
Okay.
Yeah.
That concludes the session and actually also the conference. So, okay.